Okay, good morning, everybody. So let's get started. So we're going to just finish the exercise visualization today, and we also have a quiz, right? And next Tuesday, we have exam 3 for visualization, right? That covers, all of visualization. You respond to food intake and the exercise, all right? And again, you guys just wanted to focusing on the study guides and class notes, right? To make sure that you understand all the materials or information that we discuss in class. And format is the same, right? Multiple choice and forced choose selection, and also 55 questions, right? And if you guys have any questions, I don't think we have time to do the review, but if you have any question, you can just send an email, right? Okay. So I think we talk about the fat oxidation utilization is changed during the exercise from low to moderate to high intensity exercise, right? And compared to the carbohydrate utilization, fat utilization is increased and from low to moderate intensity exercise, but decreased during the later stage, right, from moderate to high intensity exercise. And we also talk about the reason why fat utilization is increased during the early stage, and 2 reasons, right? One is the availability of fatty acids is increased because of hormonal levels, particularly catecholamines, epinephrine levels increase, and so that can stimulate lipolysis from adipose tissue, release fatty acids, and it also stimulates the intramuscular triglyceride hydrolysis, right? So they're both sources of fatty acids, are available and for oxidation in muscle, and also because of the blood flow has increased during exercise, so that can also help deliver the fatty acids from fat tissue to the muscle. And the other reason is not only the availability of fatty acids increased, but fatty acids oxidation process also is stimulated, right? Because of the pathway, you guys need to remember the pathway that stimulates fat oxidation is activated during exercise because of AMP and ATP ratio is increased during exercise, particularly early stage, right? Muscle utilize a lot of ATP, so generate the AMP. So ATP levels are decreased, but AMP levels are increased, so they're causing the ratio AMP to ATP ratio increase. And this ratio is a strong stimuli of the enzyme AMPK, right? So AMPK is highly activated because of AMP and to ATP ratio increase. That will phosphorylate ACC, and ACC is the enzyme that catalyzes the formation of a malonyl-CoA, and malonyl-CoA again is a key intermediate that control or regulates the CPT1 transporter activities, right? So if we have lower malonyl-CoA levels, and we will have higher activities of CPT1 that can transport more fatty acids from cytosol into mitochondria for beta oxidation, right? So, and two reasons to try to remember, okay? And firstly, again, availability of fatty acids increase, and secondly, the process of the fat oxidation is stimulated, particularly because of AMPK pathway is activated, right? So that is something, we talk about it for the reason why fat oxidation is increased during the early stage of the exercise. And now the later stage, and we mentioned, right, the fat oxidation actually decreased when exercise is going longer and exercise intensity increase from moderate to high intensity. And here is the reason: the lower, because of a lower fatty acids availability in mitochondria, right? That is the reason why fat oxidation is actually becomes decreased during the later stage of exercise. Because of the, as the fatty acids oxidize, increase, then we will generate a lot of acetyl-CoA, right? And acetyl-CoA is can be converted to malonyl-CoA. So when exercise intensity increase and more fatty acids oxidize and generate more acetyl-CoA, and also it's converted to malonyl-CoA. So malonyl-CoA levels actually gradually increase, right, as the exercise intensity increase. So malonyl-CoA, it's a same mechanism, right, as we described in the last slide, the diagram. So malonyl-CoA levels increase, and this increase will inhibit CPT1 activity, right? So then we'll reduce fatty acids transported from cytosol into mitochondria. So this decrease is the reason for why the fat oxidation is decreased when intensity of exercise increase, right? So again, try to remember this diagram, this pathway, AMPK pathway, right? AMPK and malonyl-CoA CPT1 pathway, right? So this pathway at early stage of exercise increase activated, and the later stage is decreased, right? So the key molecule again regulate this pathway activity is malonyl-CoA. So malonyl-CoA production is changed during the exercise, right? Early stage malonyl-CoA production increase, and later stage, decrease. Early stage malonyl-CoA production decrease, and later stage malonyl-CoA production increase, right? Sorry, I try not to confuse you guys. I'm just going to say it again. So AMPK and malonyl-CoA and CPT1 pathway, right, is a key that control fat oxidation, fatty acid oxidation. And during early stage, the malonyl-CoA production is decreased, right? So you have a more CPT1 being activated, so allow the more fatty acids being oxidized. And during the later stage, because of intensity of exercise increase, which will causing increased utilization of oxidation fatty acids and causing increased production of acetyl-CoA, and acetyl-CoA can be converted to malonyl-CoA. So that means the malonyl-CoA production is increased during later stage of exercise. That are causing the inhibition of CPT1 and inhibition of fatty acids transport into the mitochondria, right? Now let's talk about the each different type of exercise, right? Aerobic exercise. Marathon is a good example for aerobic exercise. So usually run 26 miles, right, within 2 to 3 hours, depending on how you are chained or unchained runners. And energy expenditure for running a marathon requires a 2,868 kcal, right? So that means we need to burn 750 grams of carbohydrate or 330 grams of fat for running a marathon, right, to meet the energy requirement. But you know that our body actually only has 400 to 900 grams of carbohydrate on board in a fat condition, right? We only have that amount of carbohydrate, basically the glycogen, right, and plus some blood glucose that are available for exercise, right, for energy. And also because I mentioned earlier that running a marathon, only half of our muscle actually is involved, right? So that means we only have 200 to 450 grams of carbohydrate maybe available for energy. And we need 750 grams of carbohydrate for running a marathon. So that means only carbohydrate definitely is not enough to provide energy for running marathon. So that means our muscle need to utilize both carbohydrate and fat for running a marathon, right? To get enough energy. So how can we know or estimate whether our muscle use a different fuels, whether use carbohydrate versus fat or kind of mix, right? So for this, we have a method or equation, so-called whatever, to estimate the fuel utilization in the muscle. So this actually is the it's called the respiratory quotient, right? RQ. So RQ is a measurement of a fuel utilization, right? To tell us our muscle utilize carbohydrate more or fat more or mix or whatever, right? So how how does this work? So how can we measure or recalculate, the RQ? Because of carbohydrate, like glucose, right, and fatty acids, protein, they have a unique chemical structure. So use this unique chemical structure, we can calculate. So for example, the one molecules of glucose, if it's oxidized, will generate 6 molecules of CO2 and 6 use the 6 molecules of oxygen and generate 6 molecules of CO2, right? So this is the equation that we people use to calculate RQ. So RQ usually refers to the ratio of the CO2 produced to oxygen consumed, right? So you oxidize molecules, glucose, you need oxygen, right? And you generate the product, the CO2. So this is constant, right? So for example, for a oxidation of 100% of carbohydrate or glucose, that the RQ will be 1. So this is the equation for the a complete oxidation of glucose, right? So 1 molecule of glucose will need 6 molecules of oxygen and produces 6 molecules of CO2 and 6 molecules of water. So RQ, and based on this equation, so we have for oxidizing 1 molecule of glucose, we produce 6 CO2 and use 6 oxygen, right? So RQ is 1. So and that means if our muscle just only utilize this glucose, carbohydrate, and the RQ will be 1, right? And what about fat oxidation? Fatty acid oxidation. So if we use pure fatty acids, no carbohydrate, and the RQ will be 0.7. So this is the example for palmitate, right? A palmitate is 16 carbon, and you need consume 23 oxygen and produce 16 CO2, 16 water, right? Based on this chemical structure and equation. So RQ will be 16 divided by 23, so around 0.7, right? Between 0.69 and 0.73. So so this just based on the utilization of pure carbohydrate or pure fatty acids. No, not kind of mixture, right? But the reality is our muscle usually utilize both, right? Carbohydrate and also, fat as well. So what do you expect based on that information that I just described? So RQ for oxidation or mixture of carbohydrate and fat. So what do you expect RQ, the range will be? Between 0.7 and 1, right? Okay. Yes. So if we use more carbohydrate and less fat, what do you expect? The RQ will be close to 1, right? And vice versa, if we use more fatty acids and less carbohydrate, and RQ will be more close to 0.7, right? So based on this equation, calculate RQ, then you will be able to estimate, the type of energy fuel that the muscle use more carb or more fat, or something like this. And for protein, and because protein has the nitrogen, right? So the structure, is different from the fat and carbohydrate. So the calculation a little bit complicated, but anyway, we don't need to know that detailed. But RQ for utilization of protein is about 0.818, right? So here is an example to tell us how is muscle fuel utilization estimated. So for example, for a recreational marathon runner, in the first 30 minutes, and when you measure the RQ, and that particular marathon runner has a RQ between 9 and 1, right? And after 2 hours of running, almost finished the running, and when the measure the RQ again, then RQ kind of decrease, right? Between 0.8 and 0.85. So the question here for this example is, what does the information, the RQ information, tell you about the fuel utilization in the muscle of this runner? What type of energy fuel does this runner use during the early stage, like the first 30 minutes? Yeah, more carbohydrate, right? And what about the later stage, after 2 hours? And then they switch to utilize more fatty acids, right? So, so you will be able to, I wish you will be able to use this RQ information and to tell, fuel utilization switch or whatever during the time, right? And also, you're also able to, based on the RQ measurement, make a comparison between the two individuals, which individuals utilize more fat or be able to utilize more fat or carbohydrate or whatever, right? So, okay, now let's talk about the training. So we mentioned earlier, training is able to increase the oxygen consumption, the maximum oxygen consumption, right? The capacity. So if we compare the recreational versus elite runners, that they are very different, right, in terms of the fuel utilization. So, for example, the recreation runners usually have a gradual reduction in running efficiency, right? Particularly, the later stage, they were not able to perform well compared to the elite runners. And they will have a pronounced switch of fuel utilization from carbohydrate in the beginning and to fat in the last part of the race, right? So they have a big switch, the beginning they will recreation runner will use the carbohydrate, and the later stage that they will have a big switch, utilize more, fatty acids. And also the generated high levels of lactate during the first hours of the race, right? So, and the type 2 X fiber, you guys know, right? It is anaerobic fibers and utilize more, carbohydrate, right? And generate a lot of lactate. So the type 2X fibers or anaerobic fibers are actually recruited and they produce a lot of lactate during the exercise, right, for the recreation runner. So the capacity for fat utilization actually is small, right, compared to the elite runners. And also at the high intensity exercise, the recreation runners have a reduced fat oxidation, right? Reduced ability to utilize fatty acids. So again, for recreation runners, they have a decreased capacity for fat utilization, right? They were not able to efficiently utilize fatty acids for energy, particularly during the later stage. And we know because of fat utilization is decreased, right? In general. And also they have a higher levels of a type 2X fiber recruited so then they produce actually more lactate, right? So recreation runner very easy to get fatigue. And what about the elite runners and the chained runners, right? So they usually have a gradual reduction in the running efficiency, kind of small, so they be able to efficiently, run during the whole time period of the race. So they be able to constantly use the mixture of carbohydrate and fat oxidation, right? And the switch from carbohydrate to fat utilization, particularly at the later stage, is also kind of small, right? So they be able to, utilize the mixture of the carbohydrate and fat. And they also have reduced the production of lactate during the early stage of the race, and they have a higher capacity for fat utilization. So they will be able to utilize fat during the later stage particularly, right? So that will allow them to perform well. So here is kind of experimental results, and make a comparison of a energy fuel utilization between chained and unchained runners, right? So if you look at the middle diagram, the unchained, let's look at unchained on the right side, right? Unchained runners, you can see they utilize more carbohydrate, right? 70%, right, of the energy actually from the carbohydrate, and only 25% energy from the fat. So the unchained runners, they have reduced capacity to utilize fatty acids for energy, right? So they heavily rely on the carbohydrate oxidation for energy. And if you look at the chain runners, they actually have much higher capacity of utilizing fatty acids for energy. So they be able to utilize 50-50, right? 50% of energy from carbohydrate and another 50 from fat. So so after chaining, the fat oxidation or oxidative capacity actually significantly increase. So the chained runners are able to utilize fatty acids for energy during particularly later stage, right? And another thing is important is that the consequences of the carbohydrate metabolism, right? So the carbohydrate metabolism is also different. So this is for chained runners. So chained runners are able to complete oxidize glucose, right, through the TCA cycles, so that they will have a less lactate produced during exercise, right? But the unchained runner, they have a lower oxidative capacity, right? So the most of the glucose actually being partially oxidized through glycolytic pathway and produce a lot of lactate, and much less being completely oxidized, right? So two things actually different between in terms of fuel utilization between unchained and chained individuals. First, the type of the energy fuels being utilized, right? Unchained utilize more carbohydrate and less fat utilization, and chained individuals be able to utilize more fat, right? Because they have a higher oxidative capacity. And the second thing is the metabolism of carbohydrate glucose is different. Trained individuals are able to complete oxidize glucose, right? So have a less lactate produced because of they have a higher oxidative capacity. But the untrained, they have a less oxidative capacity, so most of the glucose being partially oxidized produce a lot of lactate, right? And this is another experiment that people did to compare the fuel utilization before and after training, right? So the bottom figures showing the total energy utilization, actually pretty similar before and after, right? You use the similar amount of energy, produce similar amount of energy. But if you compare to, the before and after training in terms of the energy utilization from fat versus carbohydrate, they are actually changing. So let's look at the top figures first. This is the carbohydrate utilization, right? So the solid dot represent the after training, right? The circle, it's the carbohydrate utilization before training. So you can see the carbohydrate utilization actually decreased after training, right? But the fat utilization, you see that actually increased. So after training, the fat utilization is increased, but carbohydrate utilization is decreased. So there are actually kind of approach that we can use to improve the endurance, or exercise performance. Our bodies also can adapt to the exercise, right? In response to training. So after training, so our body physiological adaptation will also happen. So here are some of the physiological adaptation in response to training or after training. So we're able to increase the cardiovascular functions, right? So actually the three different aspects of physiological adaptation. First is the cardiovascular adaptations, right, after training. So we're able to increase the heart rate, right, or increase cardiac output, and increase the gas exchange in the lung. We get more oxygen, right? Be able to, and also increase the capillary density in the skeletal muscle, so that will increase the blood flow to the muscle tissue, right? To allow the more oxygen being delivered to the muscle. So again, the three aspects of a cardiovascular adaptation. One is to increase the cardiac output, increase, and the second is the increase exchange, gas exchange, right, to allow more oxygen to get into the body. And third is to increase the blood flow by increasing the capillary density, right, to have a more blood, get into the muscle. And a second thing, adaptation, that's something happened in the muscle cells. That is the mitochondrial numbers, right? So after training, we're able to increase mitochondrial number in the muscle fibers, right? So that will help increase capacity of beta oxidation, right? And also increase the reliance on the fat utilization. So that will allow us to able to utilize fatty acids for energy, right? And decrease reliance on the carbohydrate utilization. You know that one molecule of fat oxidation produces much more ATPs, right, compared to the glucose. So fat oxidation, it produce ATPs more efficiently than the glucose. So if we are able to utilize the fatty acids, we usually try to save the glucose, right? So the chain individuals, because of mitochondrial numbers increase, so fat utilization capacity increase. So that will allow us to reduce, to utilize less glucose, right, for energy. And that also will help us to reduce the lactate production, right? The lactate basically is associated with the fatigue, right? So fatigue is a big issue, I guess, to affect the performance. So if we have a reduced lactate production, and we can, have a less possible that fatigue will happen, right? And lastly, the muscle glycogen can also be increased after training, right? So increased muscle glycogen is also the one of the adaptation to training, right? So again, the three aspects of a physiological adaptation in response to training. So after training, we can increase the cardiovascular functions, right? And increase the mitochondrial numbers in the muscle fibers, and lastly, increase the glycogen, the storage, right? Muscle glycogen storage. Yeah, question. Yeah, the after training, so you will have all this kind of improvement, right? So muscle glycogen is, I mentioned earlier, right? It's important for the later stage of a race, particularly, right? Because of fat oxidation capacity decrease, right, during the later stage. So if you have a more glycogen store, that muscle can utilize, carbohydrate to maintain the same levels of activity. Any questions? Right? Okay, now let's talk about the post-exercise recovery period. So what happens after exercise in terms of energy fuels, storage and utilization? What happened after, like when you finish the marathon running? Glycogen is depleted, right? You use up, all the glycogen, muscle glycogen, and also the glucose and fatty acids are taken up by the muscle, so utilized for exercise, right? So insulin sensitivity in muscle actually increased during the post-exercise period, and the major sources of energy fuel is, so what is the major energy fuel that muscle use during the post-exercise period? You can Thinking about it. In the first 18 hours of a recovery period after a high carbohydrate meal. So what usually a marathon, runners will recommend to eat? What type of food? Carbohydrate, right? Yes. So high carbohydrate, high protein, right? So after finish running, and then runners eat high carbohydrate diet. So what do you think what type of energy fuels the runner will use during this recovery period? They definitely eat a high carbohydrate diet, right? You use carbohydrate or fat? And why? Fat, right? Because the priority thing that the body needs to do after exercise is to rebuild muscle glycogen, right? So you always want to save glucose for glycogen synthesis, resynthesis. So even you give them a high carbohydrate diet, you get a lot of carbohydrate from the diet, but they won't use them. They were saved for glycogen synthesis in the muscle, right? So actually they body prefer to use fat in order to save glucose for glycogen synthesis, right? So again, the high fatty acids, fat is the priority or the primary sources of energy that the body used during the recovery period, right? But the triglyceride is also being, restored, right? Within the 48 hours of recovery period. Okay, so that was the aerobic metabolism exercise. Now let's talk about anaerobic metabolism, right? So anaerobic metabolism, the main characteristics of the anaerobic metabolism is it requires a lot of energy in a very short period of time. For example, 100-meter sprinting, right? Finish within 10 seconds. So the increased oxygen delivery to muscle will not going to happen within the 10 seconds, right? So that means the muscle will have to utilize the installed energy within the muscle, right? So the energy fuels that are utilized for anaerobic exercise for ATP production mainly is intramuscular glucose, right? That means muscle glycogen, and also creatine phosphate, right? So these are the two important energy fuels for anaerobic exercise, right? Muscle glycogen and creatine phosphate. Why not liver glycogen? It also takes time, right, for liver to break down glycogen and to deliver glucose from liver to muscle. So it's not also going to happen within the 10 seconds. So everything that already present in the muscle that can be immediately used for energy, right? So muscle glycogen and creatine phosphate. And also the other important characteristic of the anaerobic metabolism exercise is that glucose is only oxidize partially, right, through glycolysis pathway, will not be completely oxidized because of the, you don't have enough oxygen, right, to complete oxidize glucose. So this type of exercise will generate a lot of lactate. And which type of fibers that you think should be involved in this anaerobic exercise? Yeah, 2X, type of 2X fibers, right, involved in this anaerobic exercise. So we wanted to have more type of 2X fibers for the sprinting type of exercise, right? Can we just take a 5 minutes break? Right, okay. All right. So again, the sources of carbohydrate and fatty acids for oxidation in skeletal muscle during anaerobic exercise, right? Mainly the creatine phosphate and glucose. So glucose basically is mainly is muscle glycogen breakdown, right? But of course, the glucose, if already present in the circulation, they can quickly uptake into the muscle, right? It that can also help. But I just wanted to let you know the fatty acids definitely is not the energy sources, right, for anaerobic exercise, because of not able to oxidize. So creatine phosphate usually is used for the first few seconds, right? And this is the equation for how creatine phosphate to break down and release the ATP, right? So it's very quick process. And the enzyme called creatine kinase, right, can dephosphorylate to remove the phosphate and add it to the ADP and to make ATP, right? It's very quick reaction. And in terms of the generation of creatine, usually creatine, our body it's able to make creatines, right, in the liver, pancreas, and kidney. And the substrate for creatine phosphate, for creatine production is the amino acids like arginine, right? This is a couple of steps, right, to make a creatine. So once creatine is made in the liver, pancreas, or kidney, then be transported to the muscle and get phosphorylated and stored in the muscle, right? So our body is able to make a creatine from the amino acids, and it also can get directly from the diet with some type of food, can also have a higher amount of a creatine, like a beef, tuna, salmon, right, and all stuff they have contain some creatine. And this just gives you some idea how energy being used during the 10 seconds, the type of exercise. So first few seconds, you see the creatine phosphate is being quickly used, right? This creatine phosphate. And after a few seconds, like 3 seconds, the creatine utilization it dropped significantly almost, but the glycogen utilization actually increased significantly. So the first few seconds, the muscle utilized mainly the creatine phosphate, and after a few seconds, and then glycogen become the main sources of the energy, right? And this just the reaction you guys know, right? For the glycolysis, the glucose being mostly produced lactate will not be completely oxidized during the anaerobic exercise. Now carbohydrate loading, diet, exercise. So we know that carbohydrate loading is very important, right? The particularly muscle glycogen that can affect the performance. So they are actually the most efficient way is just to give them a high carbohydrate diet, right? And let me see. So the purpose is particularly for the post-exercise period, right? The purpose of the high carbohydrate diet is to rebuild glycogen, muscle glycogen, and the most efficient way is just give them a high carbohydrate diet, right, to rebuild the glycogen. And high-fat diet definitely will not be able to help build up the muscle glycogen, right? So the question is how much carbohydrate is needed for building a muscle glycogen. Usually more than 70% of total calorie from the carbohydrate diet, this type of diet will be able to significantly increase the glycogen store. So the diet contains the energy, 70% of energy from the carbohydrate that will help significantly increase, right, the glycogen stored. So actually a scientist did kind of experiment to to determine how much carbohydrate is needed for increase the carbohydrate, for increase the glycogen store. This experiment done in 1967. So they give a subjects, right, 3 different diets and make a comparison which type of diet is more efficient for the glycogen, for increasing the glycogen store. First is a high-fat diet, and normal diet. Secondly, normal diet and high carbohydrate diet, right, contain 82% of energy from the carbohydrate. And this is the results, and you can see that the black bar is the high-fat diet, and red is normal diet, and green the high carbohydrate diet. And y-axis is the time to exhaustion, right? So muscle glycogen actually determines the time to exhaustion. So if you have less glycogen stored, that it will easy to get exhausted during the exercise, right? So x-axis is the glycogen, right? How much glycogen is rebuilt for the different type of diet. So you can see for the high-fat diet, feeding only able to get about 90 grams of glycogen, right? And the time to the exhaustion significantly lower, right? That means you very easily to get exhaustion. And normal diet, you'll be able to get about 180 something, right? The glycogen, and the time to exhaustion increase a little bit if you have a little bit more glycogen. And for the high carbohydrate diet, be able to gain about 400 grams of muscle glycogen, right? So then you can significantly increase the time to exhaustion, so that it takes longer time to get exhaustion, right? So so this kind of strong evidence, right, showing that increased muscle glycogen is very important to increase performance and reduce the time to exhaustion. And the carbohydrate diet is the most efficient way, right, to increase the muscle glycogen store. So there is several ways approach that we can use to increase the carbohydrate loading, right? Increase the muscle glycogen. So the first approach is the carbohydrate depletion stage, followed by a very high carbohydrate diet. For example, when you finish a training or a game, and then you give the individuals immediately a high carbohydrate diet, right? So that is the one approach that you can do, right, to increase the carbohydrate loading. And the second approach is to give the carbohydrate meal 2 to 4 hours before competition, right, before the game, like a couple hours before the game. Then you can give the individual or athlete the carbohydrate diet. And depend on the duration of the game or competition. If the game lasts less than 2 hours, and you can give them like a digestible carbohydrate food, for example, spark drinks or something, so they can immediately get the carbohydrate into the body, right? And if the game lasts longer than 2 hours, then you usually be able to give them kind of solid product, bread, bananas, energy bars. So because they were able to, you have a little bit more time, right, to get carbohydrate into the muscle. And the third approach 3, you also be able to give the carbohydrate drink during the game, right? For example, cycling or running a marathon, actually you can give them energy drink, right, during the game, so to provide the carbohydrate. Some type of game like intermittent high intensity sports. This type of sport, they have a lower intensity exercise and combined with repeated like a short distant sprinting, this type of exercise, like a football or kind of game. You can also give the carbohydrate containing drinks, right? And this can help save the some of the muscle glycogen stores, right, for the use during the few minutes of the sprinting kind of exercise, right? That's all I have for the visualization and exercise. Do you guys have any question? Yes.
So for the carbohydrate loading to increase muscle glycogen, is there like an amount per grams where if you go over then it starts having diminishing returns? Is it like the difference between having 20 kilograms of carbohydrates 2 to 4 hours before as opposed to like 100 grams?
You mean the before exercise you gave them? You mean whether the amount of carbohydrate you give will affect the performance? That's a great question. I don't think that will affect. I mean, as long as you give enough. If you give not enough, that more carbohydrate, I think it will have a better effect, right? And so I don't know, I'm not sure that will affect, but my understanding probably will not. Okay, any other questions? All right, now we have a quiz.